This is question number 3 from paper 2 of the 2020 final exam. It's a topic 6 question. We have a small ball rolling around inside of a frictionless bowl. And here's the setup. It says the normal reaction force N makes an angle of theta to the horizontal. State the direction of the resultant force on the ball. And this is all shown in this diagram. If I look at the setup here, note that the normal force, as it is defined, is perpendicular to the surface of the bowl. This is a circle, and so this tangent right here, at this point, the surface of the bowl is this tangent, and these are perpendicular. So the normal force is perpendicular to the surface of the bowl, the inside surface. And then we have, of course, the force of gravity. We're going to get into that in part B, where we make a free body diagram. State the direction of the force, the resultant force on the ball. The resultant force on the ball, we got circular motion that's going around and around in this circle. And so we know that the resultant force must be a centripetal force, and therefore it must point towards the center of the circle. Now, a lot of students make a mistake and they say that the force points towards the center of the bowl. And you can't say that because, well, where is the center of the bowl? Somewhere along this line, but is this the center of the bowl? Is this the center of the bowl? Is this the center of the bowl? It's not the center of the bowl, however you want to define that. It's the center of this circle. So you have to say that the direction of the resultant force on the ball is towards the center of this circle, defined by its motion. Okay. So you have to write it that way. Not the center of the bowl, the center of the circle, in order to get full marks there. And I hope that makes sense. Part B says on the diagram to construct arrow of the correct length to represent the weight of the ball. Okay. So I will reproduce this diagram over here. So 3A, I won't write that out, but you have to say that the direction of the force is towards the center of the circle, not the bowl. For 3B, we have this diagram, and what we have is the ball, our point here. We got a normal force that points up like this, and we're given, it's about all we're given on the diagram. We're given a dotted line here to define the horizontal. Construct an arrow of the correct length to represent the weight of the ball. So we have to try to scale the right length as well. We know that the resultant force is going to lie along this horizontal. The resultant force, F here, is going to lie this way. Remember, this is the normal force N. The only other force acting then is going to be the weight of the ball. And the weight of the ball, of course, is going to go straight down, and that's going to be mg. Now, I made this force a little bit too long, you can see. So the way that this should work is that when I have the weight of the ball has to come over here with the normal force so that the resultant is the centripetal force. I take this weight vector and I move it over here, okay? And so this is N, this is the resultant force, this is mg again. So this arrow needs to be about the same length as from the tip of the normal force down to this dotted horizontal line that they gave you. And that's what we mean by the correct length. So that when you add the vectors mg and n, you get F, okay? So that has to look like the normal force plus the weight mg is going to give you the resultant force F, which is a centripetal force. 3C, this is a show question. We want to show that this force F, Fc, is equal to mg over the tangent of theta. And remember, this was our angle theta. Okay, well, this is right triangle trigonometry. It's all right here. The tangent of theta is opposite mg over adjacent fc. And so rearranging that, I get that f is equal to mg over tan theta. Okay, that's just the simple right triangle trigonometry. So, yeah, right, tan theta You could write this out here. Tan theta is opposite mg over adjacent f, and then rearranging, you get what they ask to to show them. It's a show question, so that's what the answer you're going for, and you can use this diagram and trigonometry to show that. Okay, the last part, 3D. Now we have to determine the speed of the ball, given that the radius of the bowl is 7.5 meters. It's a big bowl. That's the radius of the bowl. The whole bowl up here is 7.5 meters. But remember, I'm down here. I'm down here inside the bowl, and this radius is going to be less as the bowl slopes in. So I'm going to call this big R. The radius of the bowl is equal to 7.5 meters. But I'm down here inside the bowl where the radius is less. Down at the bottom of the bowl, the radius is 0. So I need to find this radius right here. So that makes this problem a little bit more difficult, and it's easy to just go ahead and pop in the radius. Later we're going to see the radius R is 7.5, but that's not the right radius. As often is the case, this problem progresses. First of all, we find we work out how F comes about through the resultant of the normal force and the weight, and then we show that F is equal to mg over tan theta, and we know from part one that F is a centripetal force. So I can think now of two different expressions for this force F, and that's the key to solving the last piece, which is to determine the speed of the ball. I equate two different expressions for the force, one being the equation that I was asked to show up here. So I've got mg over tan theta. That's the force, but the force is also a centripetal force. So it's also mv squared over r. And I know I need this because I'm asked to find v. V is what I'm looking for. The m's cancel, and I rearrange this thing for v, and I will get that v is going to be equal to the square root of, what is that, g little r over tan theta. Okay? Now, what is little r, though? What is this little r down here? It's not 7.5. So you would have to come in and have a look at, we can make a triangle right here, right? We can make this triangle right here. This would be the radius of the bowl. Okay, it's a semi-sphere. So any point from any distance from the center down to the surface of the bowl is going to be this radius 7.5. So that makes little r here the cosine of the cosine of the angle that we're making with the radius of the bowl. Okay, so that means that we have that little r is equal to big R times the cosine of theta. Okay, so putting that in here, that means that V now is going to be equal to the square root of G big R cosine theta over tan theta. And since tan theta is sine over cosine, and it's on the bottom, this also could be written as the square root of GR cosine squared theta over sine theta. So this expression here is going to tell me what my velocity is. Plugging this all in, what I'm going to get is I'm going to get the square root. I'll go to exponent form now. We got G, 9.81, times R, big R, the radius of the bowl, 7.5 meters, times the cosine of 17 degrees, we're in degrees here, squared, over the sine of 17 degrees. If you plug all this into your calculator, you should get something in the neighborhood of 15.2 meters per second. Okay, and then the trick to this problem really was realizing that the radius of the bowl is not the radius of our circle. Okay, we're down here. The radius of the bowl R is up here. I got my angle theta here, and I need to find out this little r right here. Okay, so this would be the cosine of theta is going to be adjacent over hypotenuse. So r is equal to, little r is equal to big R cosine theta. Okay, all right, that's that one.